You will extend your antiderivative toolbox to trigonometric functions. The main skill is pattern recognition. Identify the function, locate its inner derivative, and choose the formula that reverses the derivative rule. These 6 formulas are not new facts floating in space. Each one reverses a derivative you already know. Pairing derivatives with antiderivatives is much easier than memorizing 12 unrelated expressions. The negative signs come from the derivatives of cosine, cotangent, and cosecant. Radians are essential because the familiar derivative formulas are valid without extra conversion factors only in radian measure. Degrees have enough complications already. Try the integral before revealing the answer. Linearity lets you integrate each term separately. The negative sign on the cosine term comes from integrating sine, while the coefficient -3 stays attached to the cosine integral. The factor 1/5 compensates for the derivative of the inner expression. This is substitution in shortcut form. The chain rule creates the 5, and integration politely removes it. This answer needs both a negative sign and a factor of 1/3. Missing either one produces a near miss, and calculus is not famous for awarding points to answers that are almost differentiable enough. When the inner function is linear, divide by its slope. You can still write a full substitution, but the shortcut saves time once the pattern is familiar. The inner expression can be nonlinear. If its derivative is present, substitution reduces the integral to one of the 6 basic formulas. The real work is recognizing the matching pair. The expression x squared plus 1 is the inner function, and its derivative supplies the x factor. The missing factor 2 becomes the coefficient 1/2. This is the chain rule running backward. The best substitution is the entire denominator, not necessarily the angle. Its derivative is negative sine, which explains the negative sign. Substitution does not care which expression looks most trigonometric. It follows derivatives. A substitution must match the whole differential, including constants. A quick derivative check catches these coefficient errors immediately, before they escape into the final answer. A trigonometric expression can play the role of u just like a polynomial expression. Once substituted, the integral may become an ordinary power rule. Trigonometry enters wearing a disguise and leaves as u to a power. The cosine factor is the derivative partner of sine. The inner derivative contributes 3, and the power rule contributes 1/5, giving the final coefficient 1/15. The secant squared factor is exactly the derivative of tangent. The added 1 remains inside you, but its derivative contributes nothing. Even constants know when to stay out of the way. Definite trigonometric integrals use the fundamental theorem exactly as before. The only new step is evaluating familiar trigonometric values at the endpoints. The derivative of sine 2x is 2 cosine 2x, and the antiderivative of secant squared is tangent. Exact endpoint values make the calculation short and clean. When x multiplies a trigonometric function, substitution may not help. Integration by parts transfers the derivative to x, where it becomes 1, leaving an easier trigonometric integral. Choosing x as you makes its derivative 1. The boundary term vanishes at both endpoints, and the remaining cosine integral equals 1. Sometimes integration by parts creates more writing only to make most of it disappear. A definite integral measures net signed area. If the graph crosses the axis, positive and negative regions can cancel. Geometric area refuses to cancel anything and counts every region positively. The graph stays above the axis on this interval, so the definite integral equals the geometric area. Notice the symmetry about the y-axis before calculating. The endpoint sign values are 1 and -1. Subtracting the lower value adds another 1/2, producing total area 1. Symmetry provides a useful visual check. Single powers of tangent, cotangent, secant, and cosecant have logarithmic antiderivatives. These formulas look less obvious, so we will derive the tangent and secant cases. Tangent becomes sine divided by cosine, and the numerator is the negative derivative of the denominator. The logarithm appears because the transformed integral is 1 over u. The extra factor secant plus tangent is chosen so that the numerator becomes the derivative of the denominator. It may look like a magic trick, but the derivative check reveals the method behind it. The tangent formula contributes the negative logarithm, and the linear argument contributes 1/4. Equivalent logarithmic forms may look different while having the same derivative. Cotangent integrates to the logarithm of sine. The coefficient 1/3 again comes from the inner linear function. At this point, the pattern should be becoming pleasantly repetitive. The secant formula always carries the combination secant plus tangent inside the logarithm. The factor 1/2 compensates for the inner derivative. The cosecant formula uses cosecant minus cotangent. The sign inside the logarithm is different from the secant formula, so keep each pair as a single memorized pattern. Secant and secant squared are not interchangeable. One tiny exponent changes the entire antiderivative, which is a lot of influence for such a small symbol. A rate integrates to an accumulated total, while dividing an integral by the interval length gives an average value. Periodic models appear naturally in temperature, production, seasonal demand, and other repeating patterns. Integrating the hourly rate gives the total production. The model is continuous, so the decimal is an estimate. A physical item count would be rounded appropriately. Calculus can produce 0.56 of an item, but the factory probably should not ship it. Average value means the integral divided by the interval length. The answer has temperature units, not temperature hours, because dividing by 6 hours cancels the time unit. Units are excellent at exposing formula mistakes. Substituting u equals the natural logarithm of x converts dx into e to the u do. The result is a product of an exponential and a sign, so integration by parts becomes the appropriate method. After 2 rounds of integration by parts, the original integral reappears. This is useful, not a failure. Move it to the other side and solve for it like an algebraic variable. Collecting the 2 copies of I produces the factor 1/2. Returning to x replaces e to the u with x and u with the natural logarithm of x. This is a rare integral that tries to come back and negotiate its own answer. Start with the simplest recognizable pattern, then move to substitution or integration by parts only when needed. A derivative check is the fastest way to confirm an indefinite integral and catch missing signs or coefficients.